Welcome to the video lecture series Digital Filter Design and its Application. Subject code is MEC103. My name is Dr. Anilesh Day, Associate Professor, Department of Electronics and Communication Engineering, Narula Institute of Technology. Sharing this course with one of the renowned professors, Professor Dr. Sholil Kumar Sannal. Professor Dr. Sholil Kumar Sannal, retired professor and head Department of Electronics and Telecommunication Engineering, Jadavpur University. Presently, Professor Dr. Sholil Kumar Sannal working as a professor in Department of Electronics and Communication Engineering, Narula Institute of Technology. This course is designed for MTech in Electronics and Communication Engineering students. This is lecture 10. In the previous lecture, lecture 9, I explained the method for digitizing the analog filter into digital filter using impulse invariance method. I find out that Hz equals to summation of k equals to 1 to n ck divided by 1 minus pk into t into z to the power minus 1, where pk are the poles of the analog filter and ck are the coefficient in the partial fraction expressions. I also explained for the high sampling rate Hz equals to summation of k equals to 1 to n t into ck whole divided by 1 minus e to the power pk into t into z to the power minus 1. Today I start with the steps to design a digital filter using impulse invariant method. Step number 1. For the given specification, find HAS, which is the transfer function of an analog filter. Step number 2. Select the sampling rate of the digital filter, that is the t second per sample. Step number 3. Express the analog filter transfer function as the sum of single pole filters, that is HAS equals to summation of k equals to 1 to n ck divided by s minus pk, where pk's are the poles of the analog filter and ck are the coefficient in the partial fraction expressions. Step 4. Compute the Z transform of digital filter by using the formula, that is Hz equals to summation of k equals to 1 to n ck whole divided by 1 minus e to the power pk into t into z to the power minus 1. So s minus pk in the analog filter transform into here 1 minus e to the power pk into t into z to the power minus 1. Step number 5. For the high sampling rate, we use that Hz equals to summation of k equals to 1 to n t into ck whole divided by 1 minus e to the power pk into t into z to the power minus 1. This is the designing steps to design digital filter using impulse invariance method. Now, with the help of these designing steps, in the next slide, I'll solve some numerical problems. The problem number 1. For the analog transfer function, H is equals to 2 divided by s plus 1 into s plus 2. Determine Hz using impulse invariance method and assume t equals to 1 second. So it is given that H is equals to 2 by s plus 1 and into s plus 2. Now, I want to add in this thing in HA is equals to summation of k equals to 1 Ck divided by S minus Pk. That is the analog filter transfer function as the sum of single pole filter. So using partial fraction, we can write that H is equals to A by S plus 1 plus B by S plus 2. Now, how do we find the value of the A and B? So, for finding out the value of the A, the denominator A is S plus 1. This S plus 1 multiplied with the value of the H's and putting S plus 1 equals to 0. So, S equals to minus 1. So, S plus 1 cancel out. Put the minus 1 over here. So, that is minus 1 plus 2, that is plus 1. So, A become 2. And to find the value of the B, denominator B is the S plus 2. So it is multiplied with the H's, that is S plus 2 into 2 divided by S plus 1 into S plus 2, where S plus 2 equals to 0. So S become minus 2. So S plus 2 cancel out. Put the value of minus 2 over here. So minus 2 plus 1, that is minus 1. So B become minus 2. So H's become A equals to 2 by S plus 1 plus minus 2 of S plus 2, taking the minus outside. So A by S plus 1 minus 2 by S plus 2. So it is look like this. H's is 2 by S plus 1 minus 2 by S plus 2. But I have to add in this thing, that is the S minus Pk term in the denominator portion. So, but it is written of the plus 1. So I can rearrange this thing, that is the S minus of minus 1. So I am rearrange this 2 divided by S minus of minus 1. In this here, it is a S minus of minus 2. So poles are, that is the pKs are, there is a two poles. One is the P1 and another is P2. So P1 equals to minus 1 and P2 equals to minus 2. So we are getting the two poles, that is minus 1 and minus 2. Using impulse invariant technique, we have if H is equals to K equals to 1 to n summation of that Ck by S minus Pk, then Hz equals to K equals to 1 to n summation of that Ck by 1 minus e to the power pkt into z inverse or z to the power minus 1. That means S minus pk is transformed to 1 minus e to the power pk into t into z to the power minus 1. So here S minus pk, it is transformed over here 1 minus e to the power pkt into z to the power minus 1. Now, there are the two poles which I derived in the previous slide. That is the two poles are, one is the P1 is minus 1 and P2 is minus 2. So using this formula, we can find the Hz equals to 2 divided by 1 minus e to the power pk. Pk is minus 1, putting the minus 1 over here. Pk into t into z to the power minus 1. Similarly, here the pk is minus 2. So 1 minus e to the power, instead of the pk, I can put the minus 2 into t into z to the power minus 1. So in this way, from h's, we can convert to the hz. Now in the question, it is given that t equals to 1 second. So put the value of the t in the previous equation. So hz become 2 divided by 1 minus e to the power pk, that is minus 1, into t, it is 1, into z to the power minus 1. And here 2 divided by 1 minus e to the power, value of pk is minus 2, t is 1, into z to the power minus 1. So we have to find the value of e to the power minus 1 and e to the power minus 2 and replace this equation in this form. That is 2 divided by 1 minus 0.3678 into z to the power minus 1 minus 2 divided by 1 minus 0.1353 into z to the power minus 1. And if I solve this equation becomes 8z equals to 0.465 z to the power minus 1 whole divided by 1 minus 0.503 z to the power minus 1 plus 0.04976 into z to the power minus 2. In this way, from the given hs, which is the transfer function of the analog filter, and t is given, that is 1 second, we finalize the what is the digital filter transfer function hz equals to 0.465 z to the power minus 1 whole divided by 1 minus 0.503 z to the power minus 1 plus 0.04976 into z to the power minus 2 using impulse invariant technique. Next slide, I am taking another problem. Using the impulse invariant t equals to 1 second, determine the hz if h is equals to 1 minus 1 divided by s to the s square plus root over 2s plus 1. So hs is given and t is also given, that is a 1 second. So I'll try to solve. Now I know ht is nothing but the Laplace inverse of the hs. So here the hs is given. I want to find it out what is the ht. So put the value of hs over here, that is the Laplace inverse of the 1 divided by s square plus root over 2s plus 1. So this equation, taking the highlighter, in this equation I can rearrange that Laplace inverse of 1 by s square plus root 2s plus half plus half. So 1 is represented in this way, plus half plus half. Now 1 by 2, can I write the 1 by 2 in this way? 1 by root over 2 whole square. So if I take this thing, it is rearranged, that is the s square plus root over 2s plus 1 by root 2 whole square plus 1 by root 2 whole square. So the first three term s square plus root 2s plus 1 by root 2 whole square, it converted into s plus 1 by root 2 whole square plus another 1 by root 2 whole square is the same as it is. So it is represented in this way. Laplace inverse of 1 by s plus 1 by root 2 whole square plus 1 by root 2 whole square. Now numerator is 1 and denominator all s plus a term is the 1 by root 2. So I have to come, this term is the 1 by root 2. So I multiplied with the root 2 and divided by root 2. So this equation becomes Laplace inverse of root 2 into 1 by root 2 whole divided by s plus 1 by root 2 whole square plus 1 by root 2 whole square. Now this equation I'm repeating once over here, so it has helped me to solve the problem. So right now I'm taking this root 2 outside. So taking the root 2 out of sight, so that is the root 2 Laplace inverse equals to 1 by root 2 whole divided by s plus 1 by root 2 whole square plus 1 by root 2 whole square. If I go for the inverse transform, Laplace transform, it will come that root over 2 into e to the power minus t by root 2 sine t by root 2. So we know let t equals to nt. So we are putting the nt in the above equation and replace the t. So root over 2, instead of this small t, I can put the nt. So nt by root 2 sine, instead of the, I am putting once nt by root 2. So this equation right now become this equation. So h of nt. Now t is given the 1 second. So I can put in the value of the t equals to 1 in the previous equation. So hn equals to root over 2 into e to the power minus n by 2 sine n by 2. Why I'm taking the hn? Because if I know the hn, I can find the transfer function hz. So if z of xn equals to xz, that means if I know the hn, I can go for the hz. Now here z of uh, xn equals to a sine n theta. So if I go for the hz equals to z of hn, that is I can take the root 2 out of side, and this is represented by the a sine n theta. So this is the Z transform. Using the Z transform property, you can solve this. This course is designed for the MTech in Electronics and Communication Engineering student, and this Z transform they are already learned in the DSP as well as the signal and system. So data I take as a prerequisite, so I am not explaining that part. So after Z transform, it become that e to the power minus 1 by root 2 z to the power minus 1 sine 1 by root 2 whole divided by 1 minus e to the power minus 1 by root 2 z to the power minus 1 cos 1 by root 2 plus e to the power minus root 2 into z to the power minus 2. Now if I replace the value of the e to the power and sine and cos term, so it will become hz equals to 0.453 into z to the power minus 1 whole divided by 1 minus 0.7497 into z to the power minus 1 plus 0.2432 into z to the power minus 2. That's so question the hs is given. We have to find it out hz. So this is the hz. So this is the answer of this problem. Now I'm explaining one more problem in this lecture. That is, an analog filter has the transfer function hs equals to 10 divided by a square plus 7s plus 10. Design a digital filter equivalent to this using impulse invariant technique where t equals to 0.27 second. Now, and start solution. Given h is equals to 10 divided by a square plus 7 is plus 10. So previous problem, first problem, it is given in the, it is factorized form is given, but here it is not given. So can I write it is the a square plus 5s plus 2s plus 10. So it becomes the h is equals to 10 by s plus 5 into s plus 2. Now what will happen? If it will come, I can write the a by s plus 5 plus b by s plus 2. And I also explain how do we get the value of the a and b. I'm explaining once again. To finding the value of the a, suppose this is the a part. So this is the denominator portion is the s plus 5. So I multiplied with the 10 by s plus 5 into s plus 2 and put s plus 5 equals to 0. So it become minus 5. So from this equation 10 by s plus 5 into s plus 2 multiplied with the s plus 5, s plus 5 cancel out. Put the value of s equals to minus 5 in the equation. So minus 5 plus 2, that is the minus 3. So 10 divided by minus 3, that is the minus 3.33. In this way, you can find out the value of the x. The similar way, you can find it out what is the value of the b. So using this partial fraction techniques, you can find it out what is the value of the a and b. But I have to arrange this thing into h is equals to summation of k equals to 1 to n ck divided by s minus pk. But it is written on the denominator is written on the s plus form. So I also explain this thing, how do we represent this s minus term. So I'm rearranging this thing, that is a s minus of minus 5. Similarly, s plus 2 rearranging as s minus of minus 2. It is given. Now we know if HAS is nothing but the summation of K is 1 to n Ck divided by S minus Pk. If I transfer to the Hz, it becomes Hz equals to summation of K equals to 1 to n Ck by 1 minus e to the power pkt into z inverse. This is the thing. That means the denominator term s minus pk transform into the 1 minus e to the power pkt z to the power minus 1, which I explained in the previous slide. Now, using this, so there is a two poles. One is the minus 5, one is the minus 2. So from there we can go for the, so hz equals to, that is a 1 minus e to the power pk, that is a minus 5 into t into z to the power minus 1. Similarly, b e to the power, this pole is the minus 2. We can put the value of the minus 2. Now we can take the value of the t, putting the value of the t, and this equation become minus 0.666 1 minus 0.3678 into z to the power minus 1 plus 0.666 divided by 1 minus 0.67 into z to the power minus 1. In this way, with the help of the impulse invariant technique, you can find the hz when in the problem the hz is given. So this is up to the today's lecture. This is the references. This is our contact details. This is the contact number for the Sanal sir, mail ID for Sanal sir. This is mail ID for me. So feel free to contact us if you have any doubt. So this is the end of lecture 10. Meet you in lecture 11. So finally, if you like, please subscribe our YouTube channel. Thank you.